Picture a semiconductor fab floor in the mid-2020s. Row after row of machines the size of small cars, each one performing a chemical or physical operation on a silicon wafer thinner than a human hair, depositing a layer here, etching a trench there, repeating hundreds of times before a single chip emerges. For decades, the companies building those machines were overwhelmingly American, Japanese, or Dutch. Applied Materials alone supplied a substantial share of the deposition and etch tools inside the world's most advanced facilities. Then the rules changed. Beginning around 2019 and accelerating sharply through 2022 and 2023, United States export controls began restricting which of those machines could ship to China. Chinese fabs would receive fewer foreign tools. Chinese toolmakers would have to fill the gap or accept a permanent ceiling. The bullish claim is that they are filling it. Companies like Naura Technology Group and Advanced Microfabrication Equipment have built production-qualified machines in core tool categories, won customers at major Chinese fabs, and turned what was once a foreign monopoly into a contested market. The skeptical counterclaim is that this closure is real only at mature process nodes and older processes, while the leading edge remains a foreign lock that no domestic Chinese supplier has cracked at production scale. Both claims contain truth. The question is, which claim describes the categories that matter most commercially? 4 rounds decided. Deposition and etch head-to-head. Full tool category coverage. Installed base and qualification inside running fabs. And the leading edge ceiling where the foreign lock is actively being reinforced. The judge scores each round on evidence, awards at least 1 round to each side, and delivers a final verdict on where parity arrived and where the lock holds. The rounds run from the category China's domestic makers entered first to the category they have not yet entered at scale. Start with the 2 operations that define chip making more than any others. Deposition lays thin films of material onto a wafer. Etch selectively removes material to carve the structures those films define. Together, these 2 categories account for a substantial fraction of total tool spending in any fab, and they are where the bullish case for domestic Chinese capability is strongest. Advanced Microfabrication Equipment has publicly disclosed in its own investor communications that its inductively coupled plasma etch tools have been qualified at major Chinese logic fabs, including the Semiconductor Manufacturing International Corporation. Those are not prototype qualifications or research bay installations. The company describes capacity shipments to multiple Chinese logic and memory fabs. Naura Technology Group has a broader product portfolio that covers chemical vapor deposition systems, physical vapor deposition systems, plasma etch tools, and thermal processing equipment. Its annual filings on the Shenzhen Exchange show revenue growth in its semiconductor equipment segment accelerating notably after 2020. The bullish case for round 1 is that these 2 companies, between them, can now supply a working set of deposition and etch tools for a mature node Chinese fab without sourcing those categories from abroad. The counterclaim requires understanding that Applied Materials is not 1 etch tool and 1 deposition chamber. It is a portfolio of dozens of distinct process modules, each tuned for specific materials including silicon oxide, silicon nitride, tungsten, cobalt, and high-K dielectrics, and for specific feature geometries. Advanced Microfabrication Equipment and Naura have credible tools in a subset of those categories, specifically the higher volume, less exotic processes. The more demanding applications, particularly atomic layer deposition for gate dielectrics and metal interconnects at tighter feature sizes, remain dominated by Applied Materials for deposition, Lam Research for etch, and Tokyo Electron for thermal and certain deposition steps. Industry analyst commentary, including from research published by firms covering the semiconductor equipment sector, describes Advanced Microfabrication Equipment's etch tools as competitive for 28 nanometer and above process nodes, with performance at tighter nodes still described as under evaluation rather than production proven. The atomic layer deposition gap deserves its own emphasis because it is not a peripheral application. Atomic layer deposition is the process by which gate dielectrics, the insulating layers that sit between the transistor gate and the channel, are deposited 1 atomic layer at a time with angstrom-level precision. At 28 nanometers, this step is demanding. At 7 nanometers and below, it is the step on which transistor performance most directly depends. Multiple semiconductor trade publications have described domestic Chinese atomic layer deposition equipment for leading-edge gate and interconnect steps as early stage or in development. Not production qualified, not running in volume fabs. In development. There is one detail that complicates the simple replacement narrative. Applied Materials' own revenue disclosures show that China became its largest single geographic market by revenue in fiscal years 2023 and 2024. Chinese fabs were buying Applied Materials tools at record rates even as domestic alternatives scaled. That is consistent with two interpretations. Chinese fabs were sourcing domestic tools where they could, and foreign tools where they had to, or they were stockpiling foreign equipment ahead of anticipated further restrictions. The public data does not separate these explanations. What it confirms is that Applied Materials was not being displaced from Chinese fabs at the revenue level, even as domestic tool shipments grew. Round 1 to China's domestic makers, narrowly and with conditions. Advanced microfabrication equipment and Naura have crossed the threshold from prototype to production qualified in core etch and chemical vapor deposition categories at mature nodes. That is a genuine achievement. But production qualified at 28 nanometers is not production competitive at 7 nanometers, and the atomic layer deposition subset is a real and documented gap. The round belongs to the domestic side for the majority of deposition and etch steps in a mature node fab. It does not belong to the domestic side for the full stack at advanced nodes. Now expand the procurement list. A fab does not run on etch and deposition alone. It requires tools across roughly a dozen major categories. Lithography to print the circuit patterns, chemical mechanical planarization to flatten surfaces between layers, ion implantation to dope the silicon with precisely controlled impurities, cleaning and surface preparation between steps, metrology and inspection to verify that each step produced what the process flow required, and packaging equipment at the back end. The bullish reading of Chinese domestic progress is that domestic vendors now provide credible options across most of these categories, that the foreign monopoly has been replaced by a foreign concentration in specific areas, and that a Chinese fab purchasing tools today can source a domestic option in the majority of line items on its list. Lithography is where this argument meets its hardest wall. There is no credible domestic extreme ultraviolet lithography alternative. Shanghai Microelectronics Equipment Group, the primary domestic lithography supplier, produces tools capable of older process nodes. Its most advanced publicly disclosed system, confirmed in Chinese government procurement notices, is a deep ultraviolet dry stepper capable of roughly 90 nanometer resolution. ARF immersion lithography, which is required for sub-28 nanometer production at competitive throughput, remains the exclusive practical domain of ASML. High-NA extreme ultraviolet systems, which TSMC and Intel Foundry are deploying for the most advanced nodes now entering production, are subject to Dutch export control regulations and will not ship to China under current policy. Applied Materials' most advanced deposition tools interact tightly with extreme ultraviolet lithography process flows, and those tools are themselves subject to United States Commerce Department restrictions expanded in October 2022 and updated subsequently. Beyond lithography, the metrology and inspection gap is underappreciated in most coverage of China's equipment progress. Metrology tools are the tools that verify whether each process step worked. They scan wafer surfaces for defects too small to see with conventional optics, measure film thickness at sub-nanometer precision, and determine whether a transistor structure has the geometry the process flow intended. KLA Corporation dominates advanced metrology globally. KLA's most recent annual report lists China as a significant revenue market, consistent with continued Chinese fab purchases of foreign metrology tools. The significance of that detail is what it implies. Chinese fabs are still buying KLA's tools, not because of preference, but because no domestic alternative has been publicly qualified at equivalent sensitivity. The coverage map for metrology has a domestic pin on it in the form of some inspection tool vendors, but the pin is at lower sensitivity than KLA's leading products, and independent comparisons are absent from public record. Chemical mechanical planarization tools from domestic vendors, including one firm reported in Chinese industry press as having installations at Chinese fabs, appear to be competitive for some layers. For the most demanding planarization steps, where surface uniformity must be maintained to within a few angstroms across a 300mm wafer, comparisons with Applied Materials' Mira and reflection product lines are not present in the public record. Ion implantation tools from King Semi, backed in part by state-linked capital, have been reported as installed at Chinese fabs and competitive for certain implant steps. High current and high energy implant tools for advanced nodes are still described by analysts as relying on applied materials and Axelis. The honest synthesis of round 2 coverage looks like this. Domestic options exist in perhaps 7 or 8 of 12 major tool categories for mature node applications. In 2 or 3 categories, the domestic tool is present but underqualified relative to what advanced process flows require. In 1 or 2 categories, including extreme ultraviolet class lithography and advanced defect metrology, there is effectively no competitive domestic product at production scale. Round 2 to the skeptics. The coverage map looks fuller than it did in 2019. That is real progress. But coverage and qualification are different measurements, and the categories with the largest leverage on yield, advanced lithography and metrology, remain foreign-dominated with no domestic alternative at scale. A fab equipped entirely with domestic tools today would run mature nodes at reduced yield and could not manufacture at sub-28 nanometers without ASML steppers. The map has more pins than before. Too many of the pins are at half height. Move to the factory floor. The most concrete evidence that domestic Chinese tools have crossed from development to deployment is the installed base growing inside running production fabs. Advanced Microfabrication Equipment has cited the Semiconductor Manufacturing International Corporation as a customer in investor communications. Naura has described multiple fab customers in its filings. The Semiconductor Manufacturing International Corporation's own annual reports and Huahong Semiconductor's disclosures describe ongoing fab expansions, and trade press reporting on those expansions has described domestic tool installations as part of the production line configuration, not confined to research bays. The argument from the domestic capability camp is that production line qualification is the actual test, and that test is now being passed at scale for mature node processes. The skeptical reading of the same data requires a distinction that fab annual reports do not draw. Qualification in a running fab has degrees. A process flow has hundreds of individual steps. Some steps have wide process windows, meaning a tool that performs at 95% of the leading foreign alternative specification still produces acceptable wafers. Other steps, the yield-sensitive ones where film thickness or etch depth must land within a fraction of a nanometer of target, have narrow process windows where tool performance at the margin directly determines how many wafers are scrapped. The most commercially consequential question is not whether a domestic tool is present anywhere in the fab. It is what fraction of the critical tight margin steps are served by domestic tools versus foreign ones. That fraction is not disclosed in any Chinese fab's annual report. The dual-track procurement pattern is documented not by domestic fab reports, but by the continuing revenue of foreign tool companies in China. Tokyo Electron and Lam Research both list China as a major revenue geography in their recent fiscal disclosures. Applied Materials China revenue, as noted, reached record levels while domestic tool shipments were simultaneously growing. This is not a paradox. It reflects what process engineers describe as rational allocation. Domestic tools for the steps where the process window allows it. Foreign tools for the steps where it does not. The two-track split is an acknowledgement, embedded in procurement behavior, that the domestic tools have not yet cleared the qualification bar for all critical steps. Round 3 is a split, awarded narrowly to the domestic side on trajectory rather than current standing. The installed base is real and growing. The qualification in running fabs is documented in company disclosures. But the dual-track procurement pattern reveals that the qualification threshold for the most yield-sensitive steps has not been fully crossed at scale. The trend line belongs to the domestic makers. The current state still belongs in part to Applied Materials and its peers. Now the round, where the foreign lock is not loosening. The leading edge is where the analysis reaches its most consequential finding, and where the dissent against the overall verdict is weakest. The bullish argument for domestic progress at advanced nodes points to trajectory. China's domestic tool investment is not aimed exclusively at 28 nanometers. Advanced Microfabrication Equipment's disclosed roadmaps describe development efforts at more advanced process nodes. The argument is that the same dynamic that drove the company from zero to Semiconductor Manufacturing International Corporation qualified in etch over roughly a decade will, given continued capital and time, repeat at more advanced nodes. Some analysts covering Chinese semiconductor policy describe the trajectory of domestic progress as genuinely compressive, not just additive. The counterclaim requires recognizing that the leading edge is not a harder version of the mature node. It is a qualitatively different engineering problem, and the gap is being maintained, and in some dimensions widened, because Applied Materials, Lam Research, ASML, and Tokyo Electron are simultaneously advancing their own tools. Atomic layer deposition for gate-all-around transistor structures, the architecture required for 3 nanometers and below, demands film thickness control at the single atomic layer level over hundreds of deposition cycles. High-NA extreme ultraviolet lithography exposes features so small that the photon wavelength is itself a limiting variable. Advanced etch uniformity at sub-5 nanometer feature sizes requires plasma control precision that is categorically more demanding than what mature node etch requires. The node gap, the distance in manufacturing generations between what Chinese domestic tools can support and what the global leading edge requires, is estimated by semiconductor analysts at somewhere between 2 and 5 generations, depending on the tool category. That range is deliberately wide because the estimate is analyst-derived, not independently audited, and because the Semiconductor Manufacturing International Corporation's internal node classification is disputed. The company has disclosed mass production at what it describes as a 7 nanometer class process achieved without extreme ultraviolet lithography through multi-patterning techniques. That is a real technical achievement. It is also more costly per wafer, less scalable, and dependent on foreign tools for the multi-patterning steps themselves. Multi-patterning is a workaround for the absence of extreme ultraviolet lithography, and it is a workaround with hard throughput and economics limits. Gate-all-around transistor structures, which the leading global foundries are in various stages of deploying for sub-5 nanometer production, require atomic layer deposition precision for channel layer deposition that domestic Chinese tool suppliers have not publicly demonstrated at production scale. Semiconductor Trade Press describes this as a genuine technical gap, not a policy artifact. The physics of depositing crystalline semiconductor material 1 atomic layer at a time over a 3-dimensional fin structure is genuinely harder than the equivalent step on a planar transistor at an older node. There is a compounding dynamic that the bullish trajectory argument does not fully account for. Every generation that Applied Materials and its peers advance their leading-edge tools, the absolute capability gap that domestic tools must close grows larger even if the rate of domestic progress is constant. A domestically built etch tool that performs at the 2019 Applied Materials level is genuinely competitive at mature nodes. It falls further behind, not closer, as the global frontier moves to gate-all-around and toward what engineers describe as complementary field effect transistors. Here are the 3 strongest reasons the Round 4 verdict could be wrong, weighed honestly. First, the verdict rests on publicly available qualification data that is almost entirely company-sourced. Advanced Microfabrication Equipment and Naura report their own qualifications. The Semiconductor Manufacturing International Corporation does not publish step-by-step tool breakdowns. If domestic tool performance at critical steps is materially better than disclosed data suggests, which is possible given that Chinese fab operators have some incentive to underplay domestic capability to maintain access to foreign tools, then the Round 3 and Round 4 verdicts may be too conservative in their skepticism of domestic progress. Second, the node gap estimate is an analyst-derived range, not a measured output. If the Semiconductor Manufacturing International Corporation's internal process development is further along at sub-7 nanometer than public disclosures indicate, and if domestic tool qualification has accompanied that development without being publicized, the leading-edge ceiling may be lower than current evidence supports. Third, the physics argument runs in both directions. The process complexity at gate-all-around and below is genuinely severe, involving heat management, plasma uniformity, and atomic-level film thickness control that are not policy problems but physics problems. Physics problems are also the category where a single material science breakthrough can compress a multi-year gap into a much shorter span. The history of Taiwan Semiconductor Manufacturing Company's own ascent from laggard to global leader argues that technology distance is not always a stable measurement. Weighed together, these 3 descents do not overturn the verdict. They locate its uncertainty. The ruling is most confident at the mature node level, where domestic tools have demonstrated production qualification across a meaningful share of steps, and at the extreme leading edge, where the gap is both technically profound and actively reinforced by export controls. The verdict is most uncertain in the 2 to 5 generation gap zone, which is also the zone of greatest commercial consequence over the next several years. Round 4 to the skeptics, without qualification. The leading edge is where the foreign lock is tightest, and where it is being actively reinforced simultaneously by policy and by continued engineering advancement at the frontier. The ceiling is real, it is hard, and it is not primarily a policy artifact. It reflects genuine engineering complexity at feature sizes, where domestic Chinese tools have not yet demonstrated production readiness. Return now to the fabs tool procurement list, the concrete anchor this analysis has carried through every round. That list, as of the mid-2020s, now carries domestic options in most line items for a 28 nanometer or above facility. The etch steps, the bulk chemical vapor deposition and physical vapor deposition steps, the thermal processing, the cleaning, and some of the planarization steps can be served by Naura and advanced microfabrication equipment in a working mature node process flow. That is genuine parity. It is not paper parity. It is production qualified, revenue generating, installed and running fabs parity. The leading edge line items on that same list tell a different story. Atomic layer deposition for gate dielectrics, advanced etch for multi-patterning and eventually gate-all-around structures, high-sensitivity metrology for defect detection at sub-10 nanometer feature sizes, and anything that interacts with extreme ultraviolet lithography remain applied materials, Lam research, and KLA territory. Not because export controls created that gap from nothing, but because the gap predates the controls, and the controls have prevented the gap from being narrowed by technology transfer. That is the thesis the contest produces. Applied Materials retains meaningful competitive separation from China's domestic toolmakers, but the nature of that separation has changed since 2019. It is no longer a broad-spectrum lock across tool categories. It is a leading-edge lock, concentrated in atomic layer deposition for advanced transistor structures, in tools that interact with extreme ultraviolet lithography, and in the metrology required to verify the results of both. In the categories that dominate a mature node fab's tool spend, domestic Chinese suppliers have earned their position. In the categories that define the frontier, they have not. The export control policy that was designed to freeze China's equipment industry at a fixed technology level instead redirected its investment, concentrated its engineering effort, and produced genuine capability in the categories where closure was achievable. The categories where closure was not yet achievable remain as gaps. Those gaps happen to align precisely with the categories Applied Materials and its peers most want to defend. The restriction intended to end the contest instead carved out the terrain where the contest is now permanently live and left unchallenged exactly the terrain where the frontier is being built. The round most open to challenge in this analysis is round 3. If you have direct knowledge of how Chinese fabs actually allocate domestic versus foreign tools at the individual process, step level, not at the procurement list level, but inside the actual process flow, the split this analysis describes may be wrong. The data on that split is the most important missing piece in public semiconductor equipment analysis. Make the case in the comments and bring the specifics. If scored, two-sided analysis with no settled verdict until the evidence earns 1 is the kind of content you want to see more of. Subscribe and turn on notifications so you do not miss the next round.